Alright, question number 6 of May 2016, time zone, paper 2, I'm sorry. Now, we're told that two cells of negligible internal resistance are connected in a circuit. So I've drawn the circuit here. We have a cell with an amp of 12 volt and another cell labeled E, but with an unknown amp. So the top cell has an electromotive force amp 12 volts and the amp of the lower cell is unknown. The ideal ammeter reads zero current. Okay, so we're asked to calculate the amp of the lower cell. All right, so if you imagine, if you use Kirchhoff's laws, so let's say we have a current from 12 volts here, right? It'll move and then it'll reach this branch right here, right? And so because the resistor and this part is parallel to the amp of 12 volts, the current will obviously separate into different branches. So um, the current going through here is 0 amps. So there's no current going through this branch. Therefore, there's only current going through this. So you can assume, of course it is true, you're not assuming. So if we label this I1, and if we label this I2, then I1 is equal to I2. So you can use Kirchhoff's laws to find the amp. I'm going to use green. So 12 minus 2i minus 4i, and I'm using I because we know they're equal, so there's no other point. There's no point using other notation. So let's see, 12 minus, this is going to be 6, going to go to the right, and 12 divided by 6 is 2, so I is equal to 2.0 amps. Are asked to find the amp of E, right? So yeah, you can use again Kirchhoff's laws. If I move from here, I consider let's see, amp minus, this is going to be 0 since there's no current moving. We come to here, so it's going to be 4 times 2 is equal to 0, so amp will be equal to 8 volts. So that's it. That's how you solve it. Pretty easy. Oh wait, finally the question follows on. Okay, I guess these are, oh, let's solve this as well. So part B, the diagram shows charge carriers moving with speed v, a metallic conductor of width L. Okay, the conductor is exposed to a uniform magnetic field. So we're asked to show that the potential difference established is across the conductor is given by V, that is capital V is equal to velocity times the magnetic field times the length. Okay, so normally when we're considering the force on what on charge carriers, we use the following. So it's in a magnetic field, and charge carriers obviously have a charge, right? So we consider force as q v times the magnetic field. Now we want to somehow transform this into a voltage equation. So we know E is equal to force over Q, right? So we can write force as EQ and substitute that in here. So EQ is equal to QVB. Q's cancel out, and we know E is equal to V over D. So we can substitute that in here. So it's going to be V is equal to, now D you can write instead of DL. So it'll be exactly VBL. So you solve part B, the first part as well. Alright, I guess that's it.